Hello, everyone, and welcome to the second in a series of 8 weekly webinars brought to you by one of IFAI's partnering organizations, North Carolina State University's Wilson College of Textiles. Today's webinar is titled Nonwovens Technology in the Production of PPE. My name is Aaron Monson. I'm the Education and Events Manager here at IFAI, and I'll be helping to host today's session. I'm joined by the IFAI team, Janelle Wells-Berkeley, Megan Furl, and Annie Castle. Also assisting with today's webinar is Melissa Sharp, Associate Director of the Zeiss Textiles Extension at the Wilson College of Textiles. A huge thank you to Melissa for project managing the development and execution of these weekly webinars. We're equally indebted to our association partners in no particular order. SEAMS, the Association and Voice of the U.S. Sewn Products Industry, ICP, Association Connecting Electronics Industries, and SPISA, the Sewn Products Equipment and Suppliers of the Americas. So in today's session, you'll learn about various nonwoven production technologies and materials and their properties and end uses. The focus will be on nonwovens used in PPE and healthcare settings, though personal use protective material will also be covered. And we are so pleased to have everyone with us today. Thank you for bearing with us as we're all working remotely, of course. We hope you'll forgive us for any technical challenge that may unexpectedly occur or any children that may unexpectedly run into the room. You will have the opportunity to submit text questions by typing them into the questions box of your webinar control panel. You may send in your questions at any time during the presentation and we'll address them toward the end of the webinar. Also, a PDF version of the slides today are available to you in the handouts portion of your webinar toolbar. And today's webinar content is provided by Stephen Sharp, Director of Engineering and Operations at Sanctuary Systems in Raleigh, North Carolina. Steve has spent more than 17 years developing man-made fibers for nonwovens and other applications. In 2001, he joined the NC State Nonwovens Institute and continued to develop new processes and products in the fiber and nonwovens industry. In 2017, Steve joined Sanctuary Systems, establishing manufacturing technologies and facilities to produce unique fiber technologies. Steve is an inventor on 6 patents and holds a BS from University of Mount Olive and an MS in textile engineering from North Carolina State University. So thank you, Steve, for being here today. I'll turn things over to you.
Thank you, Aaron, and I want to thank everybody for joining us today. I've never given a presentation on the Zoom before, so I usually do it in front of a crowd, so please bear with me. And I think I have about 30 slides here that should be informative to folks who are new to nonwovens, and we'll explain how all of these processes work to make these. What we're going to cover today, of course, is spunbond, which is a biggie, and how that's made, and that's used in a lot of these PPE products. We're going to briefly mention flash spun. Of course, melt blown is a very important one for PPE, and we're going to concentrate on that for a little while. And then we have SMS, which is the combination of spunbond and melt blown, and that's very important. We'll briefly touch on wet leg. Now, there are many types of spunbonds out there, but we're going to focus the one are most commonly used in gowns and things like that. So we're not going to cover every type of spunbond that's out there. It has a long historical history of different types of technologies and web forming, and so we won't be able to cover them all, but you'll have a good understanding of what the state of the art is now. So, but nonwovens, of course, is a large and varied industry. It has many types of web forming technologies and bonding technologies. You can use various types of web formation technologies and bonding technologies and mix and match them, of course, to make different products. And of course, you can add a lot of different raw materials from different types of fibers and different types of polymers into all those combinations. So it becomes a very large area of interest in studies, but we won't be able to cover everything today. And the Nonwovens Institute gives a lot of short courses on these kind of things, and so does INDA. So if you're really interested in becoming an expert on this subject, I suggest looking those folks up. So to start with, you know, where is all these materials coming from? I just wanted to give everybody a good understanding of that. What we mostly use is polypropylene and other olefins, polyethylenes as well. mostly because they're cheap. That's one reason. There's other ones used as well. There's nylons and polyesters and things like that. But most of these PPEs that you see out there in the market now are polypropylene in nature. Of course, polypropylene, like all, carbons are coming from the wellhead. Then the oil is then go through the fractionating column, and up here, around here is where they pull out the ethylene and the propylene to go ahead, and some other chemicals to go ahead and put into a reactor and make our polypropylene. And this is how it's generally delivered to the manufacturer in this form that you see here in the upper right. Those are chips, granulated polypropylene chips. And they're delivered in large quantities in rail cars, and they go into these very large machines that can make a lot of nonwovens very fast. So let's start with spun bond. We go right from the chip to the fabric in one step with this technology. You can see the bond patterns, which you can do different colors through pigments and things like that. This is just the end of one machine, and you can see it makes a pattern, a fiber that is very random, which gives you a lot of good porosity control, and it gives you good strength in both the MD and CD direction, although the machine direction generally has a little more strength than the cross direction does because of the way the machines move and the way the web's laid down. But we'll go through that technology here in a minute. Like I said, that it's a one-step continuous process. It can make 3 tons an hour or more on the smaller machines. So you can make just gobs and gobs of this material very fast on this machinery. The fabrics go by so quick you can't even see it. It's 600 to 800 meters a minute, sometimes 20 and 30 miles per hour. This fabric's moving onto these rollers. So it's a very tricky process to manage. You can make various basis weights for different applications, 10 to 75 GSM. The lower basis weights tend to be for hygiene and medical. We get higher basis weights. You can do more creative things with the spun bonds, such as make bags and furniture linings and things like that. But we're not concentrating on that today. For those folks that are in the general fabric industry, and 1 ounce is about 28 grams per square meter. So you can see it can be a very lightweight fabric. The fiber size that typically comes out in these fabrics are 15 to 20 microns. Like many applications, they like to get the fiber sizes down lower. It makes a better web. Also, you get more surface area, and that has a lot of advantages we'll talk about later. Now, the fibers are made, I'll show you how they're made in just a minute, and they're made in such a way that it does give them significant strength. They're not fully oriented fibers like you might find in most textiles, but they do have good strength. And the strength in a nonwoven is actually due to more of its bonding properties than anything else, but they're crystallized and oriented. Now, polypropylenes and polyolefins are generally naturally hydrophobic, which lends itself into some really good applications for PPE. You can coat with the chemicals for added functionality. Sometimes you don't want them to be hydrophobic, you want them to be hydrophilic, so you can put a chemical on there. And so some other chemicals are used, and we'll go more into that detail in a few minutes. And like I said already, the fiber orientation and distribution is very uniform. And of course, it's very economical. So this is definitely a process with economies of scale where you want to make a lot very quickly, and that's why you can keep it cheap. So you do have a lot of overhead with capital. Of course, these machines range anywhere from 40 to 50 up to hundreds of millions of dollars. They take quite a bit of time to get installed and up and running. That's where shortages right now. A simple melt blow machine is a little easier, but you get a full spun bond line, it takes time to build and get that kind of machine around grade. But you can make a lot of fabric very fast. Typically, over 80% of the cost of any one of these nonwovens is the raw material as it's brought to the manufacturer from usually Exxon or Braskem. So some examples, concentrating on our PPE today of just spun bond. Of course, we have booties and lower level protection gowns. Of course, hair nets is great. They're used to make diapers. Now, the majority of spunbond in square yardage that is made, it goes to diaper manufacturing for babies. The next biggest market, of course, is PPE and other medical fabrics. Of course, other things, like I said, hygiene, feminine products, baby diapers, adult incontinence, big markets for these folks. Then medical. Then you see some geotextiles and some other spunbond technologies where you can make a road underlayment, but also stuff for weed guard and things like that. And you see on the backs of furniture and inner linings, just to name a few. Oh, so let's get into the process. This is a diagram of by far the most common process used these days to make spunbond, and makes the best quality and very fast. It's this diagram is based on the Rectofill technology. Now I have two extruders here because my background is in bicomponent spinning of fibers, and that's kind of neat. You can make fibers that have two different polymers in them. But most of these for medical applications don't have that. So excuse the two extruders, but a lot of times just one extruder. You put the polymer in a hopper. It's pulled out a lot of times in these larger plants out of rail cars, put into a hopper, vacuum conveyed through tubing up to the extruder. There could be pigments added right here as well and other additives to help functionalize it. You have the extruder that then melts the polymer. And I'm going to show you a little bit more about extrusion in just a minute and how it works. You go into a gear pump, which meters the polymer into the spinneret. The spinneret, of course, at this point, the polymer can be anywhere from 230 to 280 degrees Celsius. Most polymers are run around 280 degrees. I'm sorry, most polypropylene is run about 260 degrees Celsius. So we'll stick with polypropylene today. Then you get these fibers that come out of these little bitty holes in what's called the spinneret plate. These holes are about a third of a millimeter, maybe half a millimeter, depending on the process. There can be, this can be 4.5 meters wide and have tens of thousands of holes in it. So you get a curtain of fibers that come out of here, and I'll show you a diagram of an actual picture in just a moment. Here we have cold air blowing on the fibers. Now in the Rectofill system, this is called the cabinet. And what they do is they pressurize this cabinet with this cold air, what we call quench air, that then creates a pressure differential between the forming area and the cabin, which pushes the air down through what they call a stretching unit. This then pulls it on this polymer as it's coming out and draws it into a fiber. Now within just an inch or two, it hardens and is fully formed. Then you fully cool it before we get into the stretching unit. Now this distance from here to here, I believe, if I remember correctly, is about 3 meters, maybe 4 meters. And then, so it is quite a tall machine, actually. And so these fibers can get to moving about 3,500 meters per minute, so they're moving very fast. And so the polymer continuously pumps and pulls. So let me show you how that works in just a minute. Of course, when it gets down here, it makes that random arrangement on the belt. We compact it. That just gives it a good enough cohesion to get it off the end of a conveyor belt, which I'll show you in just a moment, and it goes through a calendar roll, which does the bond. And that's when you see, this is where that pattern comes from. You'll see in nonwovens, where you see like a diamond pattern or an oval pattern. It's coming off this embossing roll right here. And of course, we wind it up into the big roll we saw earlier. So let's look at some actual, actually, let's look at this real quick. This is a second type of system. This is there's still some machines out there like this. What we have here is we use compressed air instead of that pressure differential to attenuate the fibers. So we bring compressed air in here, it makes a little jet, air fibers get entrained, they draw them out of the spinneret, and you get kind of the same. This does not give as good a web formation as the other one, but it's a little cheaper on the capital. But sometimes it can make fiber properties that you can't get with the other one. Usually you can run the fibers a little faster. Just a quick note on extrusion. Like I said, extrusion is how we get that pellet into liquid form before we draw it into a fiber. Here we have pellets going into extruder. It's a good animation. And of course, we run these extruder barrels. They'll have 4 or 5 different heat zones on them. If you haven't seen extruder before, here's an actual Rectofill extruder. So we got the hoppers with the side feeds, the color, etc., going in this end. We got different heaters along here. We got a motor drive. And this is a filter, believe it or not. So you actually filter the polymer with some stainless steel screens generally, and so that we don't bring contamination down into our process. And then we use a planetary gear pump that is a positive displacement pump that precisely meters the polymer downstream into the process. So we know exactly how much polymer is coming out of that spinneret in every hole. It's very important. I do a 3-hour lecture just on that, but we won't do that today. So here's an actual spinneret with fibers coming out of it. This is a small pilot line. I'm sorry, I don't have pictures of large machinery running. The folks that have that machinery generally keep that stuff pretty close to the chest, but this is a pilot line I used to run about 10 years ago. I just have lots of pictures of it. So you can see the individual fibers coming out of the spinneret holes as liquid, being drawn into a fiber. There's quench on either side for cooling, of course. Here's a cross section of an actual spinneret pack. The polymer enters the top. We got some more filtration. These are BICO distribution plates, but most for PPE medical don't have that. But you can see there's a spinneret orifice, and there's where it comes out the bottom here. And we have where we make our fiber. This is a diagram of fiber distribution because we have a single polymer stream come in. We have to spread the polymer out over the width of the machine. And this width can be up to 4.5 meters. So spreading this polymer evenly is a really big part of the technology. So let's see a video of a smaller pilot line running. It's not state of the art, but I think if you've never seen it run before, let's do bonding first. Sorry, I had the slides in my mind wrong. But anyway, so after the fiber is made, the web is made. It goes off the end of the conveyor roll, and it goes through 2 of the rolls for bonding. Now the pressure between these are heated rolls. They're generally heated with oil. And then they have a pattern on them, of course, for the embossing pattern. And you can see some examples of how it bonds nonwoven. Now this lends itself to very fast production speeds, this kind of bonding. That's why they use it. They don't use other types of bonding because it lends itself to those high production speeds. You can see different patterns they can use, and this can give you different properties. You can use round or diamond shapes. The weakest part of the fabric, it generally fails right here, as you might expect. But it's still a pretty good, strong fabric, and it goes very fast. Lots of technology here to make sure it's very even across here. The folks that make these rolls are just genius engineers and machinists. Best ones I think are made by Andritz, but there's lots of other really good ones out there too. You can also control the porosity of the fabric with some calendaring, and so that's pretty interesting when we get into filtration. All right, so here's the video. Let's get started here. So this is an older pilot line, and what's good about this video is that we can see a lot of the different aspects of the machine all at once. Even though it's an older pilot machine, developed a lot of technologies on this little thing. This is a tiny, tiny little baby machine that I think it goes through the process step. So there's the spinneret, go back. There's the spinneret. There's the air cooling coming in. Here's the draw slot. Now this one was that second technology with the compressed air draw slot. And here you can see the fibers actually coming down, hitting this conveyor belt. And that's where the web is formed. Here you can see the web coming off the end of the conveyor belt into a small calendar roll. And of course, this is I don't call that a winder, it's a sample collector, but then we wind it up into a roll. A little closer here, you can see the fibers coming down and forming on the belt. These are seal rolls to keep air from going in and out of this area. It's very important. And a close up of the fibers being spun. Cold air coming in again. And these fibers are formed within the first inch or two. You can see a little air movement there. It can be rather sensitive. There's the fibers being formed on the web. And the conveyor belt. And this is a porous conveyor belt that has vacuum under it, which helps keep these fibers adhered to the belt. That's why they don't just fly back off. There's a compaction roll. The reason why we need a compaction roll is to make the jump from the end of here to here. So it just nips it together a little bit. But this is the calendar that actually does the embossing. You can see the fibers coming now. In the no state-of-the-art systems from Ricafil, you can't even see the fibers being made because it's completely enclosed, which has much better control of the process. But this is open, which is good, so we can see through. There's the compaction roll. This is a very important item on a spun bond machine. If you have a good one, you have a lot less trouble keeping the process up. Here's going slow because we're in string up mode. You can still see that fiber being formed at a slightly thicker basis weight. I think we've seen enough of that. Let's go on to the next slide. All right, so that's spun bond. We'll talk more about those processes as we go on, and those products. But I wanted to get a note in on flash spun, which is also known as Tyvek, because it's such a ubiquitous material used for PPE. They are using it in the medical field, but you know, you've seen your own gloves are made out of it too. You see house wrap made out of it. It's a really great, what we call barrier fabric, and we're going to talk a lot about barrier fabric. And so you can't overlook its existence, even though it's made a little differently. And the reason why I don't have a lot more information on it is DuPont who makes this keeps a very, very tight cover on this process and how it's made. Very few people have actually seen it done. And so they don't choose to actually put out a lot of IP. They just keep it secret. So they've been good at that for a very long time. So it's a high density polyethylene. It's super high molecular weight, which means the polymer chains are very, very long in this polyethylene. What they have to do though is let it down a little bit of solvent or something else to get it to be a thinner as a liquid when they melt it. And then they shoot it out of a nozzle. It has this rapid expansion that's what they call it flash spinning. And when it expands, it kind of looks like you're throwing oil in the air. You know, it kind of pulls fibers in all manner of direction and really, really crystallizes and orients them. And then, of course, when it hits the conveyor belt, the solvent flashes off, and then I think they do a little bit of calendaring on it to match the fibers together. And but it makes a really neat, great fabric. And sorry I can't tell you more about it, but they are very, very secretive about it. But it's a great fabric nonetheless. And you can plasma treat it for printing, of course. So let's get into melt blown, and this is the one right now that everybody's talking about. The reason why is melt blowns, you know, has somewhat limited applications, although we've worked really hard to find new applications for melt blown over the years. But it is a pretty specialized material, and so it didn't have a lot of capacity until recently, and now they're making dozens and dozens of melt blown lines right now to help fill the face mask need and other PPE needs. It makes a very low caliper fabric. It looks almost like paper and tears like paper, so you very rarely will find it on its own. It has to be backed up by something usually. It makes very fine fibers down to 1.5 microns. So this SEM right here, so this SEM right here shows these are spun bond fibers that are in the 15 to 20 micron range, and these are melt blown fibers. So they're very, very small. You know, I think a hair fiber is typically about 75 microns. So all these fibers are quite small. Has a very good fiber orientation distribution. That means you have fibers going in all directions. They're not oriented too much in the machine or in cross direction. Sometimes a little more in machine direction. That's the direction of travel when it's being made. It has a very uniform porosity. It's about 80 to 90%, but it has barrier properties. You have to push water through it. If you put water on it, it just sits there, and you have to push it through with sometimes 40 and 70 centimeters of H2O. And we'll talk more about barrier in just a minute. And that's what's really key to meltblown for PPE. Now, it's also key for the mask for its filtration properties, and we'll talk more about that shortly. And we're going to have a whole webinar on that next week of why that works. Other things it's been used for over the years is oil absorbent, since it's made out of polypropylene, which I said is hydrophobic. It hates water, but it really likes oil. So actually, it was invented by Exxon originally, and I think they used it a lot for oil absorbents at first, but mostly to sell their polypropylene. And of course, it's been used in HEPA filters as well. Excuse me, I'll grab a drink. All right, so here's the process I think that everybody wants to hear about. Again, I apologize for the BICO to extruders. It's just this my slides are like that because I'm a BICO background. Okay. And so we got usually just one extruder coming in, a gear pump again, and then we have this die that has a triangular tip, and right on this tip is a line of holes. Again, they're about a third of a millimeter, sometimes a little bigger, sometimes a little smaller. And then we have a jet of hot air. This air is heated to the same temperature of the polymer processing, which is anywhere from, again, 240 to 280 C, usually 260 around there, Celsius. When the air comes out of here, these fibers rapidly expand with it, and they're drawn into that very fine state. Now, what's also interesting about this process is the polymer used here is really low molecular weight. It's on an order of magnitude smaller molecules than the spunbond ones. Again, a vacuum. I have videos. Let's just move on from that. Here's actual pictures of a die. There's holes all along this edge right here. Here we see the fibers coming out of the air, what we call the air knives. So we have the spinneret, the holes along this edge where the fibers pumped into. We have the hot air coming in through here, comes to there, and rapidly expands out here and draws the fiber with it. And here you can see the fibers coming out of that gap, this very, very tiny gap right here. Now what's interesting is you see this random motion where you saw the spunbond was a lot less chaotic, and this chaotic motion is really important because as the fiber comes out, it whips left and right very, very fast, and that actually helps draw it down. Not only does it draw it down, but it makes a fiber that has two different fiber sizes, so it's kind of narrow one spot, thicken another, which actually kind of helps some of its properties. So here's a pilot line I used to run in another lifetime. Now let me show you it running, and you can actually see it working. You can see the fibers are coming down here, being laid. There's vacuum under the table, all the extrusions at the top. There's the back of my head. And so this is something I wanted to stop right here. Watch the tables goes up, the forming table goes up. So this is very important for this process. So the distance between here and here is a very important setting. And the reason why is it dictates the density of the fabric, or what we call the solid volume fraction. The more dense the fabric, the less porosity it's going to have, but it's going to have a better filter. If I go up higher, I can have the less dense fabric, which have more porosity, but it might not have as fine as filtration or other properties. So just an interesting note there. We'll just let this run. See, and this doesn't need any bonding. This material, it comes out so hot that it's kind of pressed together already. We have cold air coming in here, a little bit of cold air to help it not be too hot. You can see the fibers building up. Here we are coming out of spinneret again. And here's the fabric coming off onto an auto doffing winder. And there's a roll of fabric there. And of course, again, tiny little machine. These things are generally this is 1 meter of fabric. Generally, production machines make this stuff 4.5 meters in width. Some of the smaller melt blow lines might be 1.6 or 2.4 meters for making some of the filter fabrics. So let's move on. Here we go. I just wanted to make a quick note about this. This is what's called the biax melt blown technology, or aka concentric melt blown. It makes about a 10 micron fiber. And so this is a really unique process. And the reason why I call it biax is the company that makes it is called Biax Fiber Cone. And they have a little lower fabric density than the Exxon melt blown, and it can process a lot more unique polymers. But this is kind of between the spun bond and the melt blown. Sometimes they call this spun blown, and I think that Biax calls it spun blown. And so what we have here is these little, they look like little syringe needles sticking out of the die, actually. Of course, the flat ends though, and the polymers pump through the syringe needle. Hot air comes through here and surrounds the polymer exiting and draws it into a nice neat fiber. It makes it a little less dense, and you can use that for a dirt holding layer. But I think they're having a lot of success with this and making some good filter media with it at the biax. All right, so here we go. Here's the meat of, so we got a good understanding. We got a good understanding of those two processes. So when we get into gown, this is how it's made. We actually have a spun bond section, a melt blown section, a spun bond section on the same machine. So we drop some spun bond down, then we drop some melt blown down, and then we drop some spun bond down again, and then we go through the calendar bonder. So SMS is called, and I'm sure you've heard that term. So you got spun bond, melt blown, spun bond. You get the best of both worlds. We got the melt blown barrier properties. We got the spun bond strength and flexibility, because I remember I said the melt blown doesn't have a lot of good strength on its own. So we have to put it in this composite to keep it together. They'll coat it with some super hydrophobic fluorochemicals and silicone, and this helps with alcohol repellency and also, of course, blood splatter repellency. And there's different, and we'll go over that in just a minute. It could be sterilized with radiation after the garment's made. So generally they'll make the fabric, the garment, put it in a bag and sterilize it. Usually, I heard last with gamma radiation, but there's a lot of techniques to do that. Also treated for alcohol repellency and anesthetic. And of course, as I mentioned, the water, blood, alcohol splash impact resistant. So this is a picture right off of Ricafil's website of a full-size machine that makes SMS. So this is a spun bond section. Here's the stretching unit, the extruders right here. We feed the polymer extrusion, extruder filter. There's the spin beam, the stretching unit, the quench unit, the stretching unit, the forming unit. You can see the belt goes all the way under all these sections. So we got a spun bond section, melt blown, and spun bond. Now, you'll see a lot of different machines with different configurations, spun bond, melt blown, spun bond, spun bond. So it just depends on the product, the level of protection you want, economies, why you go through that. These are melt blown sections, extruders up here, melt blown. There's a person to make you understand how big these machines really are. And of course, you can see this picture here with the large rolls coming out. So this is where they've made the roll, and then they're bringing it over here to unwind it and slit it into smaller rolls for the client so they can unwind it into their conversion process. This is the calendar section. This is the section where they might be adding some fluorocarbon or other chemicals to modify its functionality and add some of that super hydrophobicity. Also, this is the curing oven right here, and it's an Omega style, which means it's a big drum. And of course, we got a winder. I wanted to make a quick note about wet laid. Wet laid is another way of making. I think this is not as ubiquitous as the spun bond melt blown, but that's a mess. But it's like paper making. It's then hydro entangled, and I'll show you that real quick. To make level 4 garments, it can be PE coated, and it can be made a variety of short PVA fibers and polyester wood pulp fibers. So usually this is made out of a very short fiber, less than a quarter inch, and not small. And of course, it can be also treated with the fluorocarbons and things to make it. So this is a.
The animation demonstrates the action.
That. So this is a wet lay machine. It's a lot like the paper making process. You have water, you have a slurry of fibers that you want to use. Now this slurry could also have chemicals in it to help disperse the fibers. It's brought up into the box. So here's a slurry of fibers will be brought in. And this video is courtesy of the NC State Textile School. And here's the slurry of fibers coming in. Of course, when they come into the water, the water is vacuumed through this porous belt, and it leaves a layer of fibers, a very uniform layer of fibers on the belt. Now, this can then be dried, and then it can be bonded lots of different ways, but usually with these things, on the next slide, is bonded with a hydroentangler. This animation illustrates that sound. So this is a very neat machine. It's used to bond a lot of higher caliper nonwovens for wipes and some other things. The fabric's brought in, and it could be a spun bond, it could be a carded web, it could be an air laid web. In this case, we're talking about a wet laid web, and it has high pressure water jets that push through the fabric, and there's about 1,200 per half meter, so there's about 2,000 of these water jets per meter. They're about 150 microns in diameter, but the pressure of the water is about 250 bar and a little lower. You bring the pressure up as you go, or you set the fabric up. Mostly it's done on the drum. So this high pressure water causes the fibers to twirl around on each other and lock together. So next time you pick up a baby wipe, look at it, you'll see streaks in it, and it's this process right here. Here's a more close-up process. This animation is a view of the water jets. You can see the water jets pushing through the fabric once again. It's a really neat machine, and this is more like 2,000 or 3,000 psi. I could give you an hour-long lecture on just how this thing works, but just so you know it exists, if you want to look it up. So hey, we're running good on time. We only have about 10 more minutes really, so we have time for questions. So I just wanted to throw some links in here and comments about the various levels of protection, because that's what this is all about. This comes right from the AAMI PV70 for barrier compliance for gown. You got level 1, 2, and 3. These are going to be different gowns for each one of these. These might be only a spun bond with a little bit of melt blown in it. This might be a single layer SMS with some additives and things, and these are a much thicker gown. And of course, any procedure, when we get into procedures like intense surgery and things like that. I put some links in here for you guys to so you know where to go look for more in-depth information. This is the AAMI website. Melissa, can you see that? Okay. So this is the AMI put this up. I do suggest you peruse this. These links here have the standard for the surgical masks, non-surgical masks surgical masks and respirators from the NIOSH. So lots of great links here. Gown standards, where you can find the methods for testing and where to understand how that's made. So lots of great information here, right straight from the authority. Here's the FDA website. So this is the FDA about medical gown, surgical gowns, sterility, about medical gowns. Here's the level, the minimal, low, moderate risk, what those gowns need to meet to be, class 2 medical device and be sold to for that use. So lots of great information here. Here again is what I already showed you in the slide. That's how we need to do that. I wanted to show you this video, and this is courtesy of our friends at AATCC. They're here in Raleigh, soon. They're going to do some webinars just on these test methods, and these are the tests, just a few test methods that talk about that show how good the barrier actually is. And this is called a hydro head. And the reason why I wanted to show you a hydro head is the melt blown is so resistant to water, like I said, that you have to push the water through it. And its barrier properties are defined by how much pressure it takes. And so this is the standard test method to know what that barrier property is. Put the sample. This is not a non-woven, so this is used for other types of fabrics too. But so you'll see this thing start to grow. So there's a water pump under there, or some other method to increase the water pressure under there. It's pushing it up, and so you'll get a head pressure of 60 or 70 centimeters on a good non-woven, on a good SMS or melt blown before it'll fail. And what the failure's coming up here. And there's the water drips. And so it takes quite, so you can see that fabric was actually deforming before the water goes through it. Yeah. And so that's an important property of this SMS. Another one, of course, is of impact testing. And so this is where so if you look through the links I just showed you, there'll be some standard test methods for blood and water and other fluids. And we'll talk about impact and splash testing. And so what they've done here is they've taken the fabric and just hung it on what looks to be about a 30-degree plane. And behind the fabric is a piece of paper, a thick piece of paper. And what they've done with it is they've weighed it first, and then they drip the water out. And you can see the paper outline. And then when they're done here, they'll take that paper and weigh it again and see if there's anything coming through. And there's lots of other tests that prove these barrier properties out for gowns and other things like that. So, but these are just a few. Again, videos courtesy of AATCC, and they'll have whole webinars on these test processes. So I encourage you to visit their website. So, everybody's on the face mask and the respirators, and so they're two different things, face mask and respirators. So you got to be accurate in your terminology here. So I just wanted to talk to them about them real quickly. Next week is going to be much more involved in how they work and what their constructions are, and especially the filtration properties and how that works, how filters work. They're not SMS per se. There'll be lots of layers in here, but usually the layering is done when the mask is made, not from an SMS line. There can be anywhere from 3 to 5 layers. Usually the spun bond's the top and the bottom. There's a middle layer of melt blown for filtration. There'll be maybe an activated carbon layer. There may be another layer of carded web or a less dense melt blown web that will help hold dirt, especially if you're in an environment that's not like a hospital. If you're outside, you're at work, these things can block off. So there might be a dirt holding layer that essentially filters out the larger particles first, so you don't blind off your fine filtration. Of course, best masks have multiple layers of a decreasingly smaller fiber, so which makes that porosity tighter and tighter, and they last longer. Electrostatics are employed to make that 95% efficiency, and we're going to talk about that in great detail next week. So I'm not going to go into great detail right now. But just remember that surgical masks do not provide full protection for inhalation of airborne pathogens such as viruses. So they do have fluid resistance, though. So they're meant to really protect the person not wearing the mask, and a lot of times the patient. And also they are kind of there to protect from splashes or in the surgical room, in the OR. So I'm not going to go too much into face masks because we're going to spend a good hour on that next week. Couple more helpful links. Here's the CDC for NIOSH. See this, they just put this out to understand the differences between the two. So I encourage you to look through this. Here's the FDA website about face masks. Lots of great information about, okay, I'm going to make face masks. What do I do? Here's the Q&A. So I encourage you guys to, if you're going to make face masks or to buy face masks and you want to be educated, it's a little dry because it's a technical document, but it'll really help. There's the CFRs are in here. Let's see where they're at. But anyway, I'll show it to you. One sec. So CFR is the federal regulation. And this is a good outline of how the respirators are made, approval of respiratory defective devices. So this is all the steps you got to go through, and all of the definitions of what's a respirator, what does dust mean. So this is the overpowering document of what NIOSH means when they say respirator and face mask. And so please visit this, peruse it, and read it carefully. Again, if you want to make masks or if you want to understand what they're really for. And I have one more link to show you. We'll be done. Skip to the last line. And here's the sorry that link's not working. But anyway, that link was for the, let's see, that's that's part 21, 887A. That's the that's more for the surgical gown and mask being used in the OR and what they have to do to meet that spec. So with that being said, I think we're done. We have about 13, 15 minutes left. Aaron, did you want to, Melissa, did we want to field some questions?
Yeah, Steve, we can field some questions. We've had a handful of them come in, so I'll go ahead and just start reading them off to you. We have one question independently submitted by two separate people, Scott and Sharon. And the question is related to the spunbound process. And the question is, how do the fibers get randomized as they lay down?
Well, that's called deceleration. So what's happening here is, let's go back to the picture. So here we go. Here's the fibers coming down. Now up here, the fibers are moving anywhere from 3,000 to 4,000 meters per minute. They're moving very, very, very fast. So when they come out the bottom here, they have to decelerate when they hit the belt, right? And the air is also being diffused a little bit down here, which causes these fibers to kind of loop around in circles and wiggle back and forth in all directions. Unfortunately, the belt moves so fast that it kind of does pull the fibers in the machine direction a little bit. So you don't get a perfect fiber distribution in all axial directions, but you do get one about 1.3 to 1. And so just imagine these fibers are coming down. They have to slow down, so they start swirling around and wiggling back and forth this way and that way. And that's what helps with the randomization.
Great, thank you. Then we have another question from Scott, and I think this is also related to the spunbound process, but you can tell me. His question is, do spinnerets move slightly?
Say it again.
Scott's question is, do spinnerets move slightly?
No, no, they do not. They do not move at all. There's some unique technologies dating way back where there's the formation section might move, like wiggle or something and vibrate back and forth. I've never seen a spinneret itself move because it's a big heavy block and it's under a lot of pressure. So there are some unique kinetic mechanics going on in some of the older technologies up here, but they've kind of fallen out of favor because of the Reichafil technology is so good.
Okay, moving on to the next question from Chelsea Bennett. Do any of these processes use needling on their fabrics?
Oh, so needle, I think she might be referring to needle punch. Now needle punch, and I didn't mention that in here, and there are some filter fabrics made out of needle punch, but they're not generally for PPE use. They're generally, not so generally, because there's always someone doing something unique out there, but used for like water filtration and some air filtration for some like HEPA, like pre-filtering HEPA or something like that. So a needle punch line is usually a carded web. So you got a randomized short staple fiber that you thicken up to sometimes 100 GSM, 200 GSM, and then you run it through a needle punch machine. And a needle punch machine is a very different process than what we've looked at. Imagine a bed of nails that have barbs sticking up, and then the special little needles on them that have barbs in different shapes and things. And the needles meet with holes and plates, and there can be as many as 1,000 needles, actually a lot more than that, per meter of width of the line. And those needles going in and out of that fabric at a very rapid rate. And the barbs and the needles cause the fibers to kind of wrap around and lock together. And so that's kind of the way you make felt and some other air filtration media. So I didn't cover it here for PPE, but it is a unique process.
Great, thank you. We have a question from Sujit, and that question is, what is the difference between spun laid and spun bound?
Nothing. The term spun laid, or you might hear dry laid, spun laid is just a reference to this section of the process. So when you say spun bond, you generally mean I've spun it here, and now I'm bonding it with the bonder. Spun bond. Now you can use other bonding techniques. You can use the hydroentangler. You can do things like through air bonded, where a certain amount of this stuff is low melt, and you just put hot air on it and melt some of it, which bonds it together. You can do needle punching isn't generally done; it tears it up because you need short fibers for that. You can do resin bonding off this here as well. So spun bond generally refers to the calendar and the spinning. Spun laid usually refers to we've gone from spinning just how we made the web right to this point.
Okay, very good. The next question is from Jing, and the question is, I have learned about monolithic breathable film in the use of level 4 surgical gowns. Is that a non-woven process, or how does this process work?
Well, I'm not a film expert at all, so I'll just tell you what I know. You can take it for what it's worth. There are breathable films out there. There's lots of technologies that make breathable film, and I do not know them. But I have used them as a layer in protective equipment and some other things. So they can be used as a complement in a composite with spun bond and other things to make, or the wet laid material to make a level 4 garment, or something that needs to be absolutely waterproof. I've seen ice bags made with it. I'm not a film expert, but I have seen it used in composites that are with nonwovens.
Great. Okay, the questions are continuing to flow in. We've got about 7 minutes before the hour, so we'll just get through as many as we can. Here's a question from Jeffrey Harmon. Given today's high demand for PPE and increased production by manufacturers, is there an increase in manufacturing equipment demand? And if so, where are these non-woven equipment manufacturers located?
Oh, good question. That's a good question. I'm not completely sure that the spun bond demand, equipment for spun bond is increased. The reason why is because the demand for some other products that spun bond might be decreasing because of the economic issue. So there might be plenty of spun bond out there to fill the gap. Because, and also remember I said this things make so much fabric so quickly. It wouldn't take a lot to really kind of. So I think as far as spun bond machines go, I don't think you'll see a big uptick in that. Now the melt blown machines are in high demand. I've talked to Phil and some other equipment manufacturers, and they are just going as fast as they can to make as many machines as they can. You're talking about a machine that costs millions and millions of dollars, takes months and months to build, and their backlogs are definitely full with melt blown demand, especially because it's that middle layer of the mast. So Phil is located in Germany. There's some folks located in Italy that make them. The Chinese are making some of the machines that are much like the Recafilm machines. Orlicon makes some machines. Hills Incorporated down in Florida makes some machines. although they don't generally do PPE stuff. So yeah, those are the folks I know about. And there's a lot of them out there that are doing it, and they're working very hard to get the capacity out there as quick as they can.
All right, a couple more questions here. This one from James Barker. And James's question is, are melt-blown filaments continuous or broken up?
That's a good question. And let's, I don't know, you tell me. So that's the answer. It depends. For the most part, you know, in their application, you can continue, you can say they're continuous. If they get too discontinuous, you know, they do break here and there in that process. And if you get too many ends going on there, you can get what's called fly. And fly is where the fibers hit that conveyor belt and shoot off into the air, and it creates a problem for the process and the operators. Let's see if I can get back over here to the one. Yeah, so when these fibers are coming down, they can break in here, and you can get too much air going on. You can try to draw them too much, and yeah, they can break. But when they hit the belt, they take off, and you see the fuzz over here, and it gets all over the machine. You can see it all up here, and it gets everywhere, and it's a real problem. So you generally try to prevent it from breaking. Now, to say you can't find ends in there, you probably can, even with a good quality melt blown. But so it's an open question. I've heard an argument both ways, whether you want to call it continuous or discontinuous.
Cool. Okay, next question is from Elissa Decker. And fun fact, Elissa is leading a webinar on Thursday, Textiles 101, so just gotta shout that out. Elissa's question is, for melt blown, what is the best way to ensure each production lot meets a certain percentage of bacteria filtration efficiency? And what documentation can I ask my manufacturer to provide so I can be sure they are meeting a certain percentage?
Oh, so you want to make sure your BFE is high. And so you're talking about, I guess when she's talking about manufacturing, she means the melt blown manufacturer. And so that is a discussion you need, a good heart-to-heart you need to have with them. They should be providing data with what is at least called every parent roll. And a parent roll is, you know, you're making this stuff, you know, 1.6, 2.5 meters wide. It goes onto one big roll, and then it's split into smaller rolls. You should at least get data on each parent roll. So if it's fiber size, it's pressure drop, it's what's called the air permeability, it's pressure drop, it's and it's bacterial efficiency if that's what you need. So if you were the larger companies that buy this stuff have their own QC, so when they get rolls, they test them themselves. So if you were to sell Nonwovens to P&G, they test them on the other end and they'll send it back. And so you should at least be getting data on every parent roll as to what those properties are that are important to you as the user.
Okay, 2 more minutes. Let's see if we can get through one more question. The question comes from John Hall, and John's question is, who are some manufacturers in the US that produce these materials? We are a cut and sew manufacturer in Michigan and would like to start mass producing PPE.
Yeah, so this is a question that we field every day here. You know, Melissa fields it all day, every day. The Nonwovens, that's inundated by these requests. So right now, the reality is they're very hard to come by. The melt blown is pretty much sold out by every manufacturer. And I'll tell you a story where in February, I was at the filter show up in Chicago, put on by INDA, and all the melt blown was already sold out because everybody saw this coming. All the larger melt blown manufacturers are already completely booked through the end of the year. By the time the show had ended, and they were looking around for people to help them produce. But as these melt blowns come online, visit the INDA website. There are links to people. Berry Plastics is Berry Global is the largest nonwovens producer in the world. There's Vitessa, the second largest nonwovens producer in the world. But these guys sell this stuff by the millions of square meters, and they have commitments to their folks like Hilliard Health and Cardinal Health, and there's other large people that make PPE. And so it's tough to get it. It really is right now. And so I'll try to answer the questions with a link, but if you, oh, we're out of time. So if you go to INDA, they do have a list of their members that make this stuff.
I would also add to that that IFAI has a really lovely database that they've compiled that you can see at ifai.com/COVID-19 that has a suppliers database for both components and finished PPE goods.
Excellent. Thanks for chiming in there, Melissa. And Steve, of course, thank you for your answers. So we're at 1 o'clock now. So we have a lot of unanswered questions, probably a couple dozen, which is awesome. I appreciate everyone's interest and engagement. This is fantastic. What we'll do is we will take these questions, these unanswered questions, and pass them on to Steve afterwards and see what we can do to get answers to everyone after the fact, probably by email. So with that, I want to say once again, thanks so much to everyone today for this great conversation. Thank you so much to Steve for the great in-depth look at nonwovens in the production of PPE. Again, if you have any questions that you think of afterwards, aside from what's already still pending, please follow up with us via email. We'll make sure we get your question answered. In relation to next week's webinar in the series, Principles of Air Filtration Materials and Design, an email announcing registration will go out tomorrow at 10 a.m. Part 3 will be led by Steve, who's here today, and if my notes are still correct, Karen Leonis, Professor of Textile Sciences in the Department of Textile and Apparel Technology and Management at NC State. All webinars in the series will take place on Tuesdays at 12 noon Central through the end of June. And you can also find registration online at ifai.com/events. And next week's webinar is live, even though the email announcing it won't go out until tomorrow. So if you want to register today, you can certainly do that on our website. Once again, my name is Aaron Monson. I'm the Education and Events Manager here at IFAI. I'm joined by the IFAI team, Janelle Wells-Berkeley, Megan Furl, and Annie Castle. And again, assisting with today's webinar is Melissa Sharp, Associate Director of the Zeiss Textiles Extension at the Wilson College of Textiles. We are eternally grateful for Melissa's leadership on this webinar series. It most definitely could not have been put together without her. And we are also indebted to our association partners, again, in no particular order: SEAMS, the Association and Voice of the U.S. Sewn Products Industry; ICP, Association Connecting Electronics Industries; and SPISA, its own Products, Equipment, and Suppliers of the Americas. And lastly, for more information about IFAI, our events, our member resources, publications, and more, visit us at ifai.com. Our 100th annual expo is coming up November 4th through 6th, 2020 in Indianapolis. So please be on the lookout for a registration announcement in about 2 weeks. I did say lastly, but that was a lie. One more thing. Finally, a very brief 2-question survey will appear when you exit the webinar. We hope you'll take a few minutes to complete it. Your feedback is important to us and helps us to continually improve our educational content. So thanks again, everyone. We're glad you could be here with us today, and we look forward to hosting you next week. Take care, everyone.